Okay, so I just wanted to start with a basic definite integral. This is similar to problem 4 on WebAssign. So what we've done so far is do a bunch of approximations. That's what 6.3 is about approximating definite integrals. And then starting in 6.4, we have the Fundamental Theorem of Calculus, which gives us like the best tool, the tool that we're going to use pretty much for the rest of the semester to evaluate definite integrals. And so Fundamental Theorem of Calculus says to evaluate a definite integral, all you have to do is take the antiderivative and plug in two endpoints and subtract, right? As opposed to making an infinitely many tiny rectangles and trying to add them all together in a Riemann sum. The Fundamental Theorem of Calculus is like a really time-saving tool for definite integrals. So for this problem here, that's our strategy. And so the first thing we want to do is rewrite our functions so that we can take an easy antiderivative. So I'm going to write this as, the integral from 1 to 9 of x to the negative first power. That's what we'll typically do for powers of x. Now, for most powers of x, we'd add 1, right, and then divide by the new coefficient. But x to the negative first, that's the one exception to that rule, to the powers of x rule. Remember that 1 over x is the derivative of the natural log function. That means the antiderivative of 1 over x is going to be natural log x.
Right.
And so our definite integral now, when we write this, just a few things here. So the dx and the integral symbol remain until we take an antiderivative. As soon as we take an antiderivative, I'll write the antiderivative. And I want natural log of absolute value of x just to make sure we don't plug in any negative numbers. It doesn't really matter for this problem since the endpoints are 1 and 9. We won't have an issue there. So natural log of x, and then I have this evaluation bar, right? Just like a long bar here with a 9 at the top and a 1 at the bottom, reminding me I'm going to plug in 9 and then subtract when I plug in 1. So my answer then is natural log of 9 minus natural log of 1. And it's not really important for, a quiz or something like that, but natural log of 1 is 0, right? Because e to the 0th power is 1. So if I wrote like a final simplified answer, I could write it as natural log of 9. And graphically, what we've done here is we found the region below this curve. So 1 over x, it looks like this. So we started at x equals 1, so started like here maybe, and then 1, 2, 3. So up to here. So this region here would be a graphical interpretation of what we just did. And this is a good problem to just like do as a warm-up. I'm gonna try and screen share over to WebAssign. There's another question that has to do with this function. I want to take a look at here. All right, so problem 12. Problem 12 also has to do with the definite integral of 1 over x dx. And it's a true-false question. True-false questions in general, they look like they're probably pretty easy, but if they're a good true-false question, there's some sort of trick or there's some sort of important point behind what's going on here. So if we take a look at what they did here, it looks like they applied the Fundamental Theorem of Calculus. So they took the antiderivative of 1 over x, which is natural log, absolute value x. And here's their evaluation bar. So plug in 1 and plug in negative 1. Those are the endpoints. And so that would equal natural log of 1 minus natural log of the absolute value of negative 1. So that would be ln1 minus ln1, which is 0. And so we're asked, does this look good or not? And at first glance, it probably should look pretty good. I mean, that's the right antiderivative. These are the correct endpoints. Right, all this math here is correct. They haven't made a mistake. But one thing that's important when we use that Fundamental Theorem of Calculus, we need to have a continuous curve here. And if we look back, I just sketched the graph briefly. Like here's the graph. The graph of y equals 1 over x has this vertical asymptote along the y-axis. And so if we try to think about like the area that's bounded here, well, this curve goes like infinitely tall and goes down infinitely low. We're actually not allowed to apply the Fundamental Theorem of Calculus to a function that's discontinuous on that interval. So like problem 4, we're allowed to use Fundamental Theorem of Calculus because y equals 1 over x is continuous from 1 to 9. right? There's no like holes or gaps or vertical asymptotes on that interval. But from -1 to +1, that passes over that vertical asymptote there, so we're actually not allowed to use the fundamental theorem of calculus, and so that the answer to that problem would be false. So it's a little bit of a reminder that fundamental theorem of calculus, while we can use it almost all the time, really the one exception would be if there's a discontinuity in the function somewhere in the interval that we're trying to evaluate. Does that make sense?
Yes.
Sweet. Okay, so I think section 6.4 should be pretty straightforward. They're going to give you definite integrals, right? So integrals with endpoints, and you're going to use fundamental theorem of calculus. So there should be some sort of function whose antiderivative you can take. Now it could be, we could give you now definite integrals with u substitutions, right? That would sort of combine some of the skills from 6.2 with some of the stuff that we're doing now with definite integrals. Let's take a look and see if there's any questions like that in the current web assignment here. Doesn't look like we've really gone there yet, but there are a bunch of problems about properties of integrals here. Yeah, so let's maybe just talk about some of the properties of definite integrals. Most of them are pretty straightforward, but it's also one of those topics that sometimes people can convince themselves of properties that aren't true.
All right.
So first thing that'll be helpful in thinking about properties of the definite integral are to remember that the definite integral adds up a signed area. So I think last week I did a problem like this. It was like the integral from maybe like 0 to 10 of 6 minus x dx. Okay, so 6 minus x, okay, that's a linear function. Slope is -1, y-intercept is 6. So that would look something like this. And if I'm adding this up to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so if I calculate this definite integral, I don't need a diagram to understand it. I don't need to interpret it geometrically, but it's important to remind ourselves of what the definite integral does and what it doesn't do. So the definite integral for a function that's always positive, it will get the exact area underneath the curve between two x values. But here's a graph that crosses the x-axis, and so it's above the x-axis some of the time and below the x-axis some of the time. And so let's calculate this first of all. So fundamental theorem of calculus says to take an antiderivative. So that would be 6x minus x squared over 2, right? That would be my antiderivative. I don't have to worry about the plus c because fundamental theorem of calculus allows us to pick any antiderivative that we want for the purposes of evaluating the definite integral. So for convenience sake, we just choose the one where c equals 0, so we don't have to worry about that for definite integrals. My endpoints are 10 and 0, and so my answer would be 60 minus 100 over 2, so 60 minus 50. That's when, oops, type it there, it should be 0. So my upper endpoint plugged in gives me 60 minus 50. And my lower endpoint, when I plugged in 0, both of these terms are 0. And so the definite integral is 10. So geometrically, since one of the regions is above the curve and one of the regions is below the curve, what that definite integral is doing is it's taking this area up here, if we call that R1, and then this region down here, which is R2, that definite integral is calculating the area above the curve minus the area below the curve. So R1 minus R2. And because I chose a function that's pretty geometrically simple here, we could confirm that just using geometry formulas. This upper triangle has base 6 and height 6. So 1/2 base times height would be 1/2 times 6 times 6. And then this triangle down here, R2, is 1/2 base times height, and its base is 4, and its height is 4, so 1/2, 4 times 4. So the area of the upper rectangle is 18. Area of the lower rectangle is 16 times 1/2, so 8. And 18 minus 8 equals 10. Okay, so that's a little bit about area. You may see problems where they ask you to find the area of a region. Remember that the definite integral counts area below the curve as negative, area above the curve as positive. That's like the first important thing in terms of properties of the definite integral. There's some other things that we can do that will sometimes make problem solving a little bit easier. Some properties of the definite integral here. These are in the book too on page 457. So I'll go through these briefly, but try and explain why they're true. So here's the first property, definite integrals. If we integrate some function f of x from a to a, all right, so meaning we start and we stop at the same x value, that integral is 0. Right, because the volume, or sorry, the area that would be generated if we start and stop at the same area, at the same x value, we wouldn't have gone anywhere horizontally, right? We just have the height of some function. Okay, so if we start and stop at the same place, the integral will be 0. This one maybe is a little bit less intuitive. If we switch the endpoints of integration, right? So we're used to the top number being the larger number and the bottom number being the smaller number. If we swap those, the effect is going to be to just change the sign of the integral.
And this is only when b is smaller than a?
Anytime we switch them, right? So like either b is bigger than a or a is bigger than b. The relationship between these two integrals is that they'll be the same number, except one will be positive and one will be negative. And so like basically my explanation for this goes back to Riemann sums. At its core, every integral is a Riemann sum. Every definite integral is a Riemann sum, meaning that we're like adding up a bunch of rectangles, right? And my explanation for why this property would be true, if we start adding rectangles from left to right, like we normally do, using the height of the function, it's no problem. That delta x would be a positive number if we go left to right. If we go right to left, then the change in x is actually a negative number, right? And so as we calculate area of rectangles by multiplying that width times the height, each one of those rectangles would count as negative area if we go right to left. So we don't use this property very often, but like let's say you had an integral that just sort of strikes you as, you know, being sort of funny, like the integral from, I don't know, we just did this problem. So the integral from like 9 to 1 of 1 over x dx, that's gonna confuse some people. They'd be like, well, how do we start at 9 and end up at 1? So what this property allows us to do is just to rewrite it in a little bit more of an intuitive form. Be like, okay, so really what they want us to do is flip the sign and also change the endpoints. And now, like that makes a little bit more sense to start at 1 and continue till you get to 9.
Okay, now I'm with you.
Okay. I'm gonna keep that and just get rid of our little example here. These are numbers, it's not really important. They probably have names too. The names aren't important either. You just need to know that like these are things that work with definite integrals. Okay, here's the third one. It's a constant multiple rule for definite integrals. So some constant times f of x dx. And we're allowed to factor that constant out. And we could prove this a couple different ways. We could prove it just based on what we know about antiderivatives and what we know about derivatives. If it's a property of derivatives, it's also a property of antiderivatives, right? So, and if it's a property of antiderivatives, that's going to transfer through to the definite integral as well. graphically what we're talking about here, if we think about this as a transformation to the graph of y equals f of x, c f of x, it's just going to stretch that graph vertically by factor c. And so the area beneath the curve will also be stretched or dilated by that factor c. So we've probably been using this, or you've been using it at least with antiderivatives. This says we can do that from the get-go, right? So, if we wanted to do integral area below the curve of 2 x squared dx from 1 to 2, we can factor that 2 out and do the definite integral of x squared dx. Right, that's allowed. Okay, 2 more. So property 4 says that we can add and subtract definite integrals. So if we have 2 or more functions linked by addition and subtraction, we can split those into individual definite integrals. And again, like you've probably been using this. If you have a function like y equals x squared plus x, well, you can do the definite integral of x squared and the definite integral of x separately, and you'll get the same answer as if you took a single antiderivative of the function x squared plus x. And just like derivatives, I think it's important, in addition to saying what the rule says, to be clear about what it doesn't say. It does not say that if we have 2 functions multiplied together, that will equal the product of the 2 definite integrals. That is not true. So likewise, if we have f of x divided by g of x, the definite integral would not be the definite integral of f divided by the definite integral of g. If we have anything other than a sum or a difference, really the only thing that we've been able to do so far is u substitution for more complicated antiderivatives. So I guess like my summary would be, we can use the fundamental theorem of calculus if we're able to take antiderivatives. So all the stuff we did in 6.1 and 6.2 also holds for definite integrals as well. Okay, last one, and this one I think is best illustrated with a picture. This says that if we wanted to take the definite integral of some function f of x from a to b, we could do that in 2 parts. We could go from a to c, and then we could go from c to b, as long as c is somewhere in between a and b. All right, so here's how I would explain that. Let's say we have some function f, and we want to take the definite integral from a to b. All right, so we're going to find the area beneath the curve. Well, if c is somewhere in between a and b, right, then what we can do is we can take the area beneath the curve up to c, like from a to c, as our first region, and then we can go c to b as a second definite integral. And if we do both of those steps, what we've done is we've calculated the full area beneath the curve from a to b. Okay, so going from a to b is the same as going from a to c, and then from c to b, as long as c is in between a and b. That's all that last part says there. And so that's sort of a summary of some of the properties of definite integrals that show up in 6.5. Any questions about the meanings or reasonings behind those properties? And pretty much, like, that is all of 6.5, is these properties and some problems to go along with them.
I guess the question that I have would be, on number 5, what's a situation that we would use that? Why wouldn't we just take one derivative or one antiderivative?
That's a great question. And I would say, well, let me answer in 2 pieces. One, each one of these equations, like we tend to think from left to right because that's how we write things, but their equations work in both directions. So it could be that we have two integrals we can actually turn into one, because you're right, it's usually easier to do a single integral, right? And then maybe to answer in the second part, let me do an example problem here. I think I can fit it in on the side here. Okay, let's do this. How about, try to think of a good example here. Let's do this. Let's do f of x equals e to the x minus 4. So that's just an exponential growth curve that's been shifted down by 3 units. And so it'll look something like this. So let's consider this problem. Let that be x equals 1, and then actually, sorry guys, I want to make this a little bit easier. That's going to give us some tough natural log equations to solve. Let's make it a parabola. We'll make it simple. Okay, so let's do this. Let's do f of x equals x squared minus 4. Okay, so now what we have is we have a parabola that's been shifted down 4 units. So it looks something like this. And I think in WebAssign in 6.5, you'll see some problems like this where they actually shade a region in the graph. So we'll say that that's 5, that's like x equals 5, and that's x equals 0. They want us to find the total area of the shaded region there. Okay, so our first thought might be, okay, no problem. I'm going to use Fundamental Theorem of Calculus. I'll just take the integral of f of x from x equals 0 to x equals 5 and be done with the problem. And that won't work. And here's why. Remember that the definite integral will take the area below the curve as negative and the area above the curve as positive, and it will add all those things together all at once. That's not what this problem is asking. It's asking us to find the area in those two regions combined as if the area is positive, right? So to solve this problem, we're actually going to have to do two integrals. We're going to have to take the integral from 0 to whatever this intersection is here. That's going to give us a negative number, so we're going to have to interpret that area as being positive, and then a second integral for the positive area up here. If we do a single integral, it's going to subtract the bottom from the top, and we don't want that. So really what we're doing then is we're taking this interval from 0 to 5 and we're breaking it into two different intervals and adjusting the sign to give us what we want here. So what we want to do here is take the integral of x squared minus 4. The region below the curve is going to go from 0 to, okay, well, if we set f of x equal to 0, we'd get x equals 2. All right, so that intersection point would be x equals 2. And that's below the curve. We know that based on the graph. So we'd want to count the negative definite integral here. Okay, so far what I've done is I've taken this first region, which I know the definite integral is going to count as being negative. Go from 0 to 2. And I'm going to, because I want it to be counted as positive, I'm just going to put a minus sign out in front here. And then we'll add that to the definite integral from 2 to 5 of x squared minus 4 dx. So like one way to think of these properties of definite integrals is a way that you can like hack or use the definite integral as a tool to solve problems that have like a little bit more complexity than just like, hey, evaluate this definite integral. And I don't think we need to necessarily go through and solve this. It's really in the setup. I've said, all right, I want this total area here, so I'm going to do it in 2 pieces. I'm justified in doing that by this fifth property here. Is that helpful?
Yes.
I think this is a problem you probably won't see until the next homework assignment. But hi, Leslie. Thanks for joining. I mean, what I wanted to do was really just give an explanation for these properties in 6.5. If either of you have questions or specific problems that you've been working on that you want to take a look at, I'd be happy to do that.
I wouldn't mind if we went over 11 on 6.4.
11 on 6.4. Let me see if I can find that.
Because I think I know what to do, but I'm not 100%.
Are you seeing my assignment here?
I am.
Right here. Okay, great. Awesome. So actually, this is a great question because this sort of leverages one of our properties of definite integrals. Let me copy it onto the whiteboard here. So my version, definite integral from 1 to 4 of 1 plus 1 over u plus 1 over u squared du. Okay. All right. Couple ways we can do this problem. We could look for a single antiderivative for this entire function here if we wanted, or we could just do like 3 simple definite integrals. That would be probably my preference here. Let's do that just because it also illustrates some of the properties from 6.5. So the idea would be then that we can do this as 3 different things: definite integral from 1 to 4 of just 1 du, and definite integral from 1 to 4 of u, 1 over u du, and definite integral of 1 over u squared from 1 to 4. And if we can take these antiderivatives, then we can use Fundamental Theorem of Calculus. First thing, let's check and make sure these are all continuous on our interval from 1 to 4. We would have vertical asymptotes or other problems if u equals 0, but in this problem we were going from 1 to 4, so we don't have to worry about that. So let's see. The integral from 1 to 4 of 1 du, well, I'll just do that as 1 here. Okay, so that would be, antiderivative of 1 would be u. So we'll evaluate u at 4 and 0. And so that would just be 4 minus 0. Sorry, no, I want to put in zeros here. 4 minus 1 equals 3. All right, so that's the value of our first definite integral. This is our second definite integral. Well, what's the antiderivative of 1 over u? Well, we just did a problem like this. 1 over u is the derivative of natural log u, right? And so our antiderivative will be natural log u, again evaluated at 4 and 1. So natural log of 4 minus natural log of 1. And Leslie, we just did a problem like this a minute ago. Natural log of 1 is 0 because e to the 0th power equals 1. So this term here just equals 0. And so really our final answer is just natural log of 4 for our second definite integral. And our third definite integral, 1 over u squared, well, let's see. I'm just going to recopy that. So let's have that be u to the -2nd power. And so anytime we have a power of x or a power of u, as long as it's not the -1st power, we can just use our general power rule, which says add 1 to the exponent. So -2 plus 1 is -1. And then multiply by the reciprocal of that new power. Right, so u to the -2nd, we added 1 to the exponent, and then we divided by that new exponent. Well, 1 over -1, that's just -1. So really what we have here is negative u evaluated at 4 and 1. So negative u with 4 plugged in is -4. And then we're going to subtract negative u with 1 plugged in. So -4 minus -1 is -3. Okay, so then to finish our problem, we can just add these things together. So we have 3 and minus 3. It's kind of nice. Did I do that right? Yeah. 3 and minus 3 will cancel, and our final answer will just be natural log of 4. Before I finish this problem here, I did this in 3 separate steps. I'm not necessarily recommending that that's like the best way to do that. We could also just go term by term in our antiderivatives, right? So if I take the antiderivative of 1, I get u. If I take the antiderivative of 1 over u, I get natural log u. If I take the antiderivative of 1 over u squared, I get minus u. Evaluated those endpoints of 4 and 1. And so if I calculate it this way, I do it all at once. It's a little bit more, it's like less work to write down, but more things to do all at once. So my upper endpoint then would be 4 plus ln 4 minus 4. That's my upper endpoint. And my lower endpoint, plugged in 1, I have 1 plus natural log of 1 minus 1. And let's see, if I do that, I get some nice cancellation, cancels, these cancel. I get natural log of 4 minus natural log of 1. And natural log of 1 is just 0. So I get the same answer if I do all my antiderivatives in a single step. Welcome back, Ben. All I did is I redid the problem with a single definite integral sort of as it's written. And I was saying like it's not better or worse to do it this way. If I do it this way, I get a single antiderivative with 3 terms. I just want like antiderivative of 1 is u, antiderivative of 1 over u is natural log u, antiderivative of u to the negative second is negative u, right? Mm-hmm. Oh boy, I made a mistake here, guys. I'm sorry. Go back and edit the video now. This should be negative u to the negative first power there. All right. So our third antiderivative has an error now. So instead of 4 minus 1, or negative 4 minus negative 1, I should have negative 1/4 minus negative 1 over 1. I forgot my exponent here. Okay, so let's see, how does that affect the problem? Negative 1/4 minus negative 1. So that's negative 1/4 plus positive 1. That would be positive 3/4. Okay, so then my final answer should be 3 plus ln 4 plus 3/4. And likewise, in my version up here, that should be the negative first power. And so this would be negative 1/4. And right here should be negative 1. Sorry about that. Thanks. Like my summary on this problem. If you have a whole bunch of things added together, feel free to do them individually if you'd like, right, as separate definite integrals, or feel free to do them all at once. The one mistake I see quite a bit is when you have a complicated antiderivative, like I do right here, and plug in the upper endpoint, and plug in the lower endpoint, we're going to subtract this entire expression with the lower endpoint plugged in. So when you do that subtraction, I know it's a little bit messy here, I put parentheses around the entire thing when I plugged in x equals 1, and that's really important. A very common mistake I see is people do everything right. They plug in the upper endpoint, they put a minus sign, and then they plug in like u equals 1, and u equals 1, and u equals 1, but they only end up subtracting the first term because they forgot the parentheses around that antiderivative. So just make sure you do that. Any other problems you guys would like to take a look at?
That was the only one I had on 6.4 that was giving me problems, and I haven't gotten into 6.5 yet.
Yeah, to me, that looks like one of the more challenging ones from that problem set. Cool. I think then maybe I will call this good for now. I put a video in the video section from last week. I did all the problems on quiz 6.2. You should be able to find that in D2L. I know those were some of the more challenging problems that we've seen so far. We're going to do some more of that U substitution using definite integrals a little bit later in the chapter. So some of that stuff will come back a little bit later. Yeah, anything else that you guys would like to see for videos?
I'll watch everything that you put up.
Oh,
Yeah,
sweet.
I have to.
I'll do yeah, I'll do some some home improv theater videos for you guys' entertainment. All right, guys. Well, I guess I'll